Hi, in this video we'll talk about the cross-correlation function, which is a really useful tool to help us in multivariate time series to be able to decide on how many lags that we should include in a model. Otherwise, you would just have to use trial and error and just to include all types of different values for the lag. And this cross-correlation function plot, we'll talk about the plot in just a little bit, and this calculation really does help us make that decision easier. So let's talk about it here. First of all, the definition, what is the cross-correlation function? It's defined as the cross-correlation between variables xt1 and xt2 at lag k. Let's back up just a second here and talk about this xt1 and xt2, just the notation. Remember, in this chapter, the notation that we're using is that your first subscript, t, for here it's t, but the first subscript represents time, and the second subscript represents the variable number. And this variable, xt2, the first variable represents time, the first subscript represents time, the second subscript represents the second variable. At lag k is the correlation, that's the regular correlation coefficient, calculated for all possible ordered pairs, xt plus k, comma 1, again, first variable, t plus k, where k is the lag, and, remember it's an ordered pair, so there's your first variable, comma, here's your second variable, xt2. So this is the second variable, and at time t. Notice that this first variable has, for the first subscript, the time plus this, whatever the lag is that we're talking about. So we've got to get that set in our minds that this first variable is k time points ahead of the second variable. Now, one thing I'm going to say about that too, it could be that it's behind. And that's going to depend on whether that lag is positive or negative. And we're going to see that clearly in an example. But just keep that in mind. Here's the general formula. There's the definition of it. But how does that look in a formula? Well, I'll admit it looks pretty bad, but it's involved. But if you'll take a look at it, you'll realize, well, wait a minute, that's not all that different from just the regular correlation coefficient formula. It's just got a bunch of subscripts in it here, and it makes it look worse than it really is. But here's the general formula. It's given by rho hat of I comma j. Now, let me give some more notation here. I comma j are just the variable numbers. So it's not this notation up here. This notation is variable I and variable j. It's not time. At lag k equals a summation, just like it does in a regular correlation coefficient. You sum up all of these cross products divided by the square root of the deviation squared. And it will be adding from t equals 1 to n minus k, because you can't go any further. There's a limited number of pairs that are even k lags apart, which we've seen that idea before as well earlier in the book. Okay, now let's do this. Instead of just going through read through every subscript, notice the overall layout. You've got this x sub I, variable I, right? Variable I minus x bar I, x variable j minus x bar j, divide by, here comes the square root of the deviation squared, square root of t equals 1 to n of xi minus xi bar squared. Same thing for j, variable j. Square root of t equals 1 to n of xj minus x bar j squared. So that's really, while it looks like a bad formula, it's not that different, as I said, from the correlation coefficient, which we learned about a long time ago in the textbook when we first find autocorrelation. So you've seen this idea before. It's just now in a different setting to where we've got two variables involved. And that's why we're saying here rho hat of I comma j. And then we've got this lag involved as well. Okay, so here's an example. Let's use this crazy looking general formula and see if we can plug in some numbers and make things look a little more little more clear to us. So row hat of 1, 2, remember that's variable 1, variable 2, of k calculates the correlation coefficient based on a bunch of ordered pairs, and here they are. It would be, notice the form of this. Let's look at the second variable throughout. So, or yeah, the second subscript. X, comma 1, x2, x, comma 1, x2. So we've got variable 1 and variable 2. So that's easy. Now let's look at the first subscript. That's of course going to contain the time component. That's what we had said up here, right? Okay, so I want to do it this way. Let's look at the second variable first. I think that'll be easier to do instead of looking at the first. Look at the second variable, and we're talking about time point 1. Well, that's going to be paired with the first variable at time point 1 plus k. Let's go to the second ordered pair. Variable 2 at time point 2 paired with variable 1 at k lags ahead of 2. Let's keep going. Third ordered pair. Variable 2 at time point 3 paired with variable 1 at k time points ahead of 3. Keep going. Finally, we get to the end. This looks a little strange, but it's going to make sense. Second variable, n minus k time points at time point n minus k, which notice that matches up with this sum n minus k for the same reason. You can't go any further than n minus k. So this is the last ordered pair that's possible. N minus k, this is paired with variable 1 at k time points ahead of n minus k, which puts you where? Right at n, because n minus k plus k equals n. Okay, better. I think that helps a little. Now, what'll really help us is if we say, all right, let me make up a lag number. Let's let the lag be k equals 2. If k equals 2, and we're looking for row hat 1, 2 of 2, that is the cross correlation between variables 1 and 2 with a lag of 2, then we're going to calculate the correlation coefficient based on this set of ordered pairs. You can look up here as a guide. And again, we'll start with the second variable. We've got x1, 2. That's the second variable at time point 1, paired with first variable at time point 3. So it's 2 time points ahead. Let's go to the second ordered pair. Variable 2 at time point 2 paired with variable 1, 2 time points ahead, because the lag is 2. Let's go to the third ordered pair. Second variable at time point 3. That'll be paired with the first variable, 2 time points ahead of 3. 3 plus 2 is 5. Keep going until you get to the end. Remember we had said that's n minus k comma 2. Maybe this will help a little bit here. Second variable, n minus 2. That's as far as you can go. And that will be paired with the first variable, 2 time points ahead of n minus 2. n minus 2 plus 2 puts you right at n. And there's the set of possible ordered pairs. And those are the ordered pairs that the cross correlation function uses in order to calculate the correlation coefficient. Okay, now let's change our lag to -3. I had mentioned earlier that that's going to make a difference in the way we interpret this. Let's take a look at it. Let's talk about it now. It was the difference between ahead and behind. And this, notice what I'd said here is that for lag k equals 2, what we have is that we're pairing variable 2 with variable 1 2 time points ahead. It's going to be right the opposite for k equal -3. When k is -3, then row hat 1, 2 of -3 considers the ordered pairs. Okay, same thing we've done before. Let's look at the second variable because that sets the time. And we're apparently looking at time 4. And you might be wondering, why did we start at 4? Well, here's why. Because our lag is -3. So if we go, remember the formula is 1 plus k. So if we take 4 plus -3, that puts us back at 1. So we have this second variable at time 4. That's paired with the first variable 3 time points behind the second variable. 4 minus 3 is 1. Let's go to the second ordered pair. Second ordered pair at time 5 paired with the first variable 3 time points ago. 5 minus 3 equals 2. Let's go to the third ordered pair. Second variable, time point 6, that will be paired with the first variable 3 time points ago. 6 minus 3 is 3. And then finally, out at the end, we have the second variable at time point n. That'll be paired with the first variable at 3 time points ago from n, and that's at n minus 3. So that's the way that we interpret this formula, the way we calculate this formula. Notice the difference between the positive lag and the negative lag. That's really important. Let's do one last thing too. What would happen if k equals 0? If k equals 0, then go up to our formula here and replace k with 0. And what do we have? We have x11, comma x12, x21, x22. We're going to write this out. If we let k equals 0, then what we have are the ordered pairs x11, x12, x21, x22, x31, x32, and that goes all the way out to the end, which would be x n1, comma x n2. So in other words, there's no lag. Variable 2 is paired with variable 1 at the very same time point, 1 and 1. Second order pair, same type of thing. Variable 2 is paired with variable 1 at the very same time point. Here that time point is 2, and so on. This is just the regular Pearson's correlation coefficient, the one that you've probably worked with in other courses in a non-time series setting. Now what we'll do next is we'll take a quick look at the calculation that we use in R in order to calculate the correlation coefficient, because obviously that's going to be a mess if we were to do that by hand. So that'll be next. Okay, as we mentioned before, let's talk about the way to calculate the cross-correlation function by using R. It's very simple. You'll see right away here the R syntax for calculating the cross-correlation function is just CCF of variable 1, we'll call it x1, comma, second variable, x2. And that calculates your cross-correlation function. That'll give you a plot. So a plot of the CCF is called the cross-correlation plot. So not a real fancy name. Sounds about what you'd think it would be. And you really interpret a cross-correlation plot the very same way you do an autocorrelation plot, meaning that a big spike at various lags, or whatever lag, gives you an indication that that could very well be a lag that you should include in the multivariate time series model, because the cross-correlation function is picking up a strong correlation at that lag. So pretty straightforward. Notice that that lag could be on the positive side or it could be on the negative side, and you would proceed accordingly. Now, one last thing before we close here. It's very important to realize that R calculates the cross correlation function the very same way that we have. We've defined it. And that is that the time shift happens on the first variable. But there are other authors and possibly other software packages who do the opposite, meaning that they calculate the correlation coefficient, the cross correlation coefficient, using the time shift on the second variable. Okay? And if that's the case, you're going to have to reverse your syntax. In other words, instead of saying CCF x1, x2, you would turn that around and say CCF x2, x1. So just keep that in mind, and this is the end of the topic of the cross-correlation function, and hope that helps, and it's really a neat topic, and as I said, it's really more of just an extension of our Pearson's correlation coefficient, but it's specifically for this case of multivariate time series. Hi, welcome to Chapter 10, which is on multivariate time series modeling. Multivariate time series models are important because just like in multiple linear regression, sometimes we need more than one variable to be able to make good predictions of a dependent variable. The same thing is true in time series modeling. A lot of times you have another variable that's related to the process or the topic at hand, and having that second variable can be very instrumental in getting good forecasts. So that's why it's important. Happens a lot in economics. You have heard of the term leading economic indicator. Well, that is an example of a second variable that could be very valuable in a time series model. That's why we need to cover this carefully. Chapter 10 has two pieces to it because there are two types of multivariate model that we'll look at. One is MLR, multiple linear regression with correlated errors. That's what this video is about. And then later on, there'll be a video about the second type, which is VAR model. That stands for vector autoregressive model. So let's move on and talk about this topic for this video, which is MLR with correlated errors. Okay, this example is example 10.1 in your textbook. It's called business sales. There's a data set in TSWGE called B sales for business sales. I've got this code highlighted here. I've even got the plots down here below, so we'll just look at that in a second. But here's what we have. Sales, that's what we're trying to predict. Predicting sales. Sales, everything is in thousands, so sales is one. Now, how do we predict sales? Well, advertising expense could be very valuable in predicting sales. Now, notice we've got two different types of advertising. We've got TV advertising and we've got online advertising. Both of those could be valuable in predicting sales. Not only that, but we've got a third independent variable called discount, and the amount of discount of maybe a promotion with various discounts. That could also be very important in predicting sales. So we've got these three independent variables trying to predict this dependent variable of sales. Now in this example, you'll see that not only do we want to look at these three variables, but we also want to look at lagged versions of each of those variables. Meaning that last month's advertising expense, or maybe even 2 months ago, may have more effect on today's sales than an advertisement that just happened yesterday, because maybe enough time hasn't passed for it to take effect. So that's why these lags are super important to look at it in various ways. Okay, so when I plot those four plots, here's what we end up with. Upper left would be sales. When I look at that, I don't really necessarily know how to describe that pattern. Upper right would be advertising, TV advertising. Lower left would be online advertise. And lower right would be discount. Notice that so the first three patterns kind of look all the same. I can't make much out of them. They definitely look like time series data sets and plenty of randomness about them, no doubt about it. But if I were to try to look at plots 2 and 3 and say, oh, I can see how that relates to sales. I can't do that. Now, plot D, the fourth one, has a very non-random pattern about it, and that makes sense because someone at the company is saying, all right, we're going to run this discount for a certain amount of time, then we're going to hike it up, then we're going to keep this discount the same for a while, then we're going to tank it down. So it's got a pattern about it that is more predictable than the other three. I don't know that I would call it predictable, but it definitely does not look like the other three and doesn't look like a random time series plot. So there's the data that we're working with here. Okay, here's what we're going to do next. We will do our first regression. Remember, MLR, multiple linear regression, we'll set the data to be B sales, set our sales variable, add TV, add online, and discount. Then we'll do a linear model, just a regular linear model. Not saying this is the best way to do it, but let's start there. So LM for linear model, sales is our dependent variable, that's the Y, tilde. Then here come your independent variables, add TV plus add online plus discount. Of course, plus doesn't mean sum. It just means include these three independent variables. And let's run that. And then look at the residuals. We're going to fit those residuals with an AR. We set that to be for P to go anywhere from 0 to 8, and we didn't let Q have a chance. We were just trying to model it as an AR model, which is fine. And it selects, you can see here, for P to be 7, right? And there are the phi coefficients for those 7 parameters. These residuals will be stored in MLR fit because that's what we named it. And let's do that. What we're going to do next is we're going to do an ARIMA. Remember what that stands for. ARIMA gives it the chance to be non-stationary. So autoregressive, integrated, moving average, right? That's a P, a D, and a Q, right? And you can see that coming into play here because ARIMA, then the data set called sales, that's the dependent variable, sales, that's Y. Then order equals C. Here's our P, D, and Q. P is 7 because that's what we were told by AIC.WGE. Q is 0, and so is D. And that is our order. And then we put these three together, C bind, so add TV, add online, and discount. And then let's run it, and we're going to get a table of values, coefficients, along with their standard errors. Now, strangely, we don't, for the first time in the book, first time in the text or in video, we don't have a p-value. So the software does not give us a p-value, but that's going to be okay. We're going to be able to estimate one, or estimate the significance of this t-statistic. And it is a t-statistic. Remember, in multiple linear regression, if you're looking for the significance of the beta coefficients, what do? You take that t-statistic, divide by, or you take that parameter estimate, divide by its standard error, and that's what gives you the t-statistic, right? Now, we're not going to have to worry about these AR coefficients. Those don't mean anything. Neither does the intercept, of course. What we care about are these three independent variables: add TV, add online, and discount. Now, just as I said before, we don't have a p-value. So what we're going to do is we're going to take this estimate of the parameter, which is 0.07, and divide by the standard error, and we get as an estimate of our t-statistic, and it's tiny. 7 divided by 0.07 divided by 0.34 is not even close to 0.5. So that's going to be a very non-significant t-value. So is add-on line, the same situation, negative 0.09 divided by 0.2. So is discount, negative 0.15 divided by 0.13. It's a little bit above 1, still very insignificant. And therefore, this model has not been very impressive. Just to confirm that our table values do what we thought they should have done, let's take a look at some plots here of those residuals. And remember, if it had been a good model, these residuals should look like white noise. Let's run that, and we can see right away that that does not really look like white noise. Looks to, it's just, there's pattern about it. And notice that the sample autocorrelations are, many of them are well outside the limit lines. There's actually a sinusoidal behavior look to it. And so that's how we know for sure that we don't think that this is white noise. We also could do the Young box test. And remember, the Young box test has for the null hypothesis of white noise. So that means that you're hoping for white noise. So you're hoping for a very high p-value, which is a little unusual. Seems like we're usually looking for low p-values, but we want a high p-value. Let's run that and see what we get. We get a very tiny p-value. So we can't reject. So we do reject the null, which means it's not white noise. That's for k equals 24. Remember, the default is k equals 24. That's how we like to test this, is at k equals 24. We'll also do it for 48, and we get a similar response. Very significant rejected null. That's not white noise. That did not work. Well, maybe we should put time in. Maybe we should put a trend. Maybe time has something to do with it. So we'll let t go from 1 to 100. We do the same type of thing, except we add in, for an extra independent variable, t. And to save a little time here, we'll just go pretty quickly through this. We see that we get an AR with an order of 6, so p equals 6 when fitting the residuals. Let's do our fit equals ARIMA again and look and see what the table values do. And you see that they do something similar as before. Actually, though, t looks like that's the trend, the time variable, is 0.046 divided by 0.014. That could be, that's above 2. Anything above 2 we would consider to be significant. That one actually has a chance, but let's continue to see if we feel like this model as a whole is going to be very valuable. Add TV still is a very small t statistic. So is add online. So is discount. Maybe it's coming up a little bit, but it's just not that significant. Let's look at our plots again and see if we have anything that looks more like white noise, or maybe the sample autocorrelations have improved. I don't think so. We still have a similar look as last time. And we'll let the Young box prove that to us. Notice I didn't say this in the last one, but you've got to give the order of the AR for this, and we get a very significant result, which means that we reject the null, and that's suggesting that we do not have white noise. Let's do it again for k equals 48. Again, reject the null. This is not white noise. That says keep modeling. Well, as at the outset we had said, lagged variables would probably be a good way to go. And that's what we're going to do here. So for lagged variables, the way that we'll lag our variables, instead of doing it by hand, not really by hand, but there are a set of code that you could use to manually lag your variables. But you don't have to do that, because you can use dplayer to help you lag. And all you do is, interesting syntax here, so dplayer ::, lag b sales, add TV, comma 1. That says create a new variable that looks back 1. So that's creating lag 1 for add TV. Do the same thing for add online. Do the same thing for discount. Or it looks like we're not lagging discount. it sort of wouldn't make sense to lag discount anyway. Discount is something that's going to be pretty present, pretty current, so it doesn't make sense to do that anyway. Plus, the way that plot looked for discount, it's one that we're not having a lot of hope in the first place. So that is how we defined our lagged variables. And then we defined new variables. We're going to call add underscore TV1 our lagged advertising for TV, and do the same type of thing for online. We'll call it add underscore online 1. So we have new variable names, and they're the lagged variables. Now let's do linear model again, MLR fit, where we let sales, of course, be our dependent variable. Then notice what we're putting in for the variables. Add underscore TV1, that's the lagged variable, plus add underscore online 1, that's the lagged variable, lag 1, plus discount with no lag. Data equals B sales. And let's run that. And then let's fit those residuals. Looks like we have order 7. Now let's do the fit equals ARIMA, giving it order 700, and see what the values look like out in the table. Remember, we don't care about the coefficients AR through AR1 through 7. We don't care about intercept. Let's look at add TV, add online, and discount. Add TV1. Now look, when we take 3.43 divide by 0.6, that goes in like 7 times or something. That's a really significant T value. All of a sudden, this looks like a very significant variable. Same thing for add online, even more so. 8.11 divided by 1.24. That goes in nearly 7-ish times or something like that. A discount, maybe a little bit of, I don't know, a little bit above 2. Again, we're not too crazy about that variable anyway, just because of the plot. And it's not that impressive, especially compared to those 2 variables that we just saw. So this is looking better. Let's look at the plots now and see if the plots look more like white noise. Yes, possibly. I know that the way this is scaled, it's kind of hard to tell by that. That leaves no doubt. This appears to be white noise. All the values are definitely within the limit lines. So that's a good look. Let's try the Young box test. Again, we're hoping for high p-values, and we do get it. We get a p-value of 0.28. That was for k equals 24. Let's try k equals 48. The p-value is even higher, 0.63. This is looking like a more promising model. Why? Well, we added lagged variables. One last thing we could do. Remember we had put trend in before, and it was the only variable that was significant when we didn't lag anything. So it would be worth putting trend back in. Maybe there is a trend in this data set. So let's give it a chance. So we do the same type of thing we did before, except we're just going to add trend to this right here in this step. In this step right here, we say MLR fit equals LM sales tilde T plus, and then everything else is the same. So let's do that. Run that. Then let's let AIC fit the residuals, and it's going to pick a P equals 7. Then we'll do fit ARIMA, order 700, and look at the table. Again, we don't care about the ARs. We don't care about intercept. We do care about everything after that, though. So for T, that's the trend. Not T as in T statistic. That might be unfortunate notation. T as in the trend or time. 0.006 divided by 0.038, that's about 2. So that's borderline, really. That's borderline. I wouldn't necessarily say that that's super impressive, especially compared to add TV and add online. Those stay extremely significant. Add TV 1, add online 1. Those are lag ones, of course. Discount still hanging in around the 2 line. It's actually below 2 this time. Discount's not looking good. And really T could go either way. So if we're a little bit uncertain, why don't we let some plots help us out here to help make a decision? Looks to me like the autocorrelations still stay in between the limit lines. Let's check the Young box test, hoping for things greater than 0.05, and it's 0.26. So we would not reject that null. That is support of white noise. Do the same thing for k equals 48. Stays up at 0.62. So really, this is a adequate model. There would be nothing wrong with this model. I guess you'd have to make the decision about whether to keep T or not. But it's not a bad model. But really what we've learned from this example is, wow, including lagged variables makes a big difference and is something that we should always think about. Now, the last thing. Here's a good question. Who was it that made up a lag of 1? We just made that up. I don't know if we made it up. Maybe we had already taken a peek at what I'm about to show you. But couldn't it be that maybe 2 time periods ago, we didn't define anything. Maybe, I don't know if this is in weekly data or monthly data. I forgot that. But 1 week ago versus 2 weeks ago versus 3 weeks ago versus 4 weeks ago, those could all have different impacts on today's sales. So how do we know that 1 week ago is what we should have looked at? Maybe we should have looked at 2 weeks ago. Maybe that would have even been better. Maybe looking at 3 weeks ago may have even been better. Of course, there's finally a point out there to where you wouldn't expect there to be much impact. But this is too judgmental. This is subjective. We need something to help us out, and that's what the cross correlation does. So let me show you some plots real quick of the cross correlation function. So CCF is what that stands for, cross correlation function. Add TV and sales, and it's really like an autocorrelation function, and you're just looking for a spike. And we see it. Remember, here's lag of 0. And the very tallest spike is back at -1. Well, that's exactly what we put in our model. And that was for advertising TV. Let's do the same thing for ad online. And we again see a spike at -1. That would make us want to put in a lag of -1. And let's check, just for fun, discount. Kind of the same strange looking plot. I wouldn't necessarily say, oh wow, look, there's the lowest point is back at -3. I'm going to put that in. Yeah, but it's not that much different than the ones around it. Discount's just a strangely behaving variable. But that's how the cross correlation function is a great, easy plot to plot. You just saw the syntax for it, and it can give you a hint as to where there would be a value that you might want to take a look at to be a candidate lag. So this is the topic of MLR with correlated errors. Really interesting and really valuable, and something, especially in economic type data, that's just one of them. Economics and finance would definitely have a lot of value in using this idea of multivariate time series. That's not the only thing. We're going to see an example next where it's about something non-financial, and that would be melanoma and sunspots. But that's for later. But I hope you enjoyed that. I hope that clears some things up. I know that was a lengthy example, but an important one, and I hope that helped. See you next time.